Okay, so our next talk is going to be given by Nicolas van Kempen, and it's going to be on reconsidering a classic paper on reconsidering custom memory allocation.
Testing is working, okay. All right, thank you for the introduction. This is joint work with, I'm Nicolas, and this is joint work with Emery, Berger, and we're working at the University of Massachusetts Amherst. So let's start this talk by rewinding the clock 24 years back to 2002. And so some events are familiar. In 2002 was a multiple of 4 years ago, and there was a World Cup. It was co-hosted by Korea and Japan, and depicted here is the opening game of France and Senegal, which Senegal famously won 1-0, eventually leading to France being eliminated before they even made it to knockout stage. So on the technical side, your favorite search engine might have been Yahoo. So for the nostalgic, there's in June 2002, sorry, this is what Yahoo looked like. I was 4 years old, so I don't actually remember what Yahoo looked like, but this is what it did. And so on the OS side, your operating system might have been Windows XP. It came out in late 2001, and 2002 is really when it became widespread. And so your desktop might have looked like this. If you were Team Apple, or you were looking to buy an Apple computer, this is what the apple.com website looked like. And so you might have been browsing on this eMac, which is advertised at $1,100, which if you convert to today's money, surprisingly, is actually around $2,026. Coincidences. So if you're on your $1,000 eMac or your Windows XP computer, looking for academic papers that are memory related, searching on Yahoo for those papers, you might have stumbled upon this paper named Reconsidering Custom Memory Allocation from Berger, Zorn, and McKinley, which was published at OOPSLA 2002. And so a common software recommendation in 2002 was to write your own custom memory allocator with the expectation that it would outperform the system default. And so this paper was reconsidering that expectation. And in fact, they reconsidered it so well that it won most influential paper 10 years later, again, from OOPSLA. And there's a few, while receiving the award, there's this citation with a few relevant words here. So until 2002, it was taken for granted that application-specific memory allocators were superior to general-purpose libraries. And so what that paper did is, reconsider that expectation and found that that assumption was not well-founded, and that in at least some cases, the general-purpose allocator was actually able to match or outperform handcrafted allocators. So let's take a step back and see what exactly we're talking about. So we're talking about mostly, again, native languages, so C, C++, Rust. And here's a snippet of a C++ function, a very simple snippet of what a function might look like. So it'll first allocate n objects of a certain size, do some kind of processing, and then free those objects. And there's two costs that are associated with these operations. There's costs that are associated with these operations, and highlighted here are the costs to actually allocate the objects and the cost to actually free the objects. And those were the two costs that people mostly focused on, at least back then, because they thought that those were the slow parts of the programs. And so Emery's paper, Emery, Benjamin, and Catherine's paper, basically talked about the strategies that people were using to actually make this faster. And so they placed these custom allocation strategies in two general buckets: per class allocators and region allocators. So now I'm going to give a brief overview into what each kind of these allocators are. So first, per class allocator, like the name implies, is per class. So every time you have a class that you want to use it for, you need to write your own code to enable it for that class. And so even in C++, which makes it a little bit easier because you can override new and delete, there's still a pretty high engineering cost to it, right? For every object, you have to write your own code. And so how it works is, first, you have a free list. Typically, those work with a free list of recycled objects. So you need a head node and then pointers to the next node. And then first looking at free, what happens when you free? Well, instead of freeing and returning memory to the underlying allocator, it'll instead push it on top of the free list simply. And then when you allocate, well, if you didn't have anything on the free list, you'll have to revert back to malloc. But if you did have a node ready to be recycled, then you can just use that instead of having to allocate again. And so one thing to note with this strategy is that the actual number of new and delete operations doesn't change. You call the new the same amount of times. What does change is how many times you actually call the underlying malloc or free. And so again, at the time, people thought that that was the expensive part. And so people thought that, well, if we avoid calling malloc, we'll save some cycles. And so that's the idea behind per class allocators. Now, let's talk about the second family, main family of custom allocation strategies, which are region allocators, which actually we'll see in this talk a little more interesting. They're also called arenas, bump pointers, chunk allocators. And so again, I have this simple C++ snippet which allocates n objects into a vector. This monotonic buffer resource is the C++ name for region allocation. They couldn't make it simple, of course. And so essentially how it works is when you call malloc a first time, instead of only allocating a single object, it'll allocate a bigger chunk. And so in this case, it looks like there's space for 2 objects. So on the first malloc, it'll allocate a size for 2 objects and only return to you the first slot in that chunk. The second time you call malloc, it'll give you the second slot, right? And then the next time you call malloc, it'll allocate a new chunk, in this case, maybe even bigger, and again, give you the first slot, and so on and so forth, right? And so essentially, it chunks allocations as it goes. So how do you free in this with this strategy? You don't. So this is where the main trade-off is. You essentially don't free until you're completely done using this arena and until every allocation is basically ready to be disposed of. So if you can't free individual objects, how do you reclaim the memory? And so this happens in some kind of either reset function or in the C++ snippet that I put up there, it happens at destruction of that buffer resource. And so essentially, it frees all the chunks one by one. And so one thing to notice here is that there is actually a reduction of operations in this scenario, because instead of calling, let's say you had 10 objects, let's say over 2 chunks, instead of having to call free on 10 different things, you can actually call free twice, right? And so you're saving a few on these reduced operations. So again, Berger, Zorn, and McKinley looked at these 2 strategies, and they concluded that, well, for per class allocators, it wasn't any better than general purpose allocation or naive allocation, meaning, again, just calling malloc free directly. While region allocators actually could provide some benefits, and in 2002 it was up to 44%. Now, enough talking about the past. Today is 2026. So some things have changed. Some things have stayed the same. In fact, it's still the World Cup, and France is playing Senegal in their opening game today at 1 p.m. So I'm not sure who's talking at 1 p.m., but I expect all of you to tune in the game instead. Your favorite search engine, Yahoo. Let's be honest, no one uses it anymore. Everyone has moved on, and everyone uses AI to search for things nowadays. So here's a picture of the Claude, window. And of course, again, on the technical side, there's been a lot of updates to software, hardware, etc. So the original study uses a Pentium processor with 200K of cache and 300 megabytes of memory. Of course, today that'd be absurd. So we update this with a modern processor with modern cache sizes of memory, 200x the cache size, and 400x the size of memory. Allocators have also changed a lot. So at the time, the baseline was the Windows default allocator, labeled here Win32, and the state of the art was dlmalloc. And today, what we use as the baseline is the Linux default allocator, here glibcmalloc, and we select 2 high-performance state-of-the-art allocators, jemalloc and memalloc. And one fun fact is that actually, dlmalloc, through a series of evolutions, is now today the Linux default allocation. So what was the state-of-the-art then, kind of, is now the baseline. And then finally, we extended the original study with a few more benchmarks, namely from Clang and Blender, that represent modern workloads. So what do the results look like today? So first, per class allocators. So again, in 2002, didn't really matter. Well, we kind of joined this conclusion. So on this, so our conclusions roughly match those of 20 years ago. So on this highlighted benchmark, for the best allocator, which in this case is memalloc, we see that per class allocation only gives you a 2% improvement, which is pretty little. And again, this is considering that the actual cost of implementing these per class allocators is very high. So high cost for 2% performance improvement, not really worth it. And so we actually extended this and calculated an upper bound. So how much can per class allocators even possibly save you at all? And so this is what it looks like. And so if you focus on the high performance allocators, again, jemalloc and memalloc, at most these per class allocators will save you roughly 10%. But again, this is on a micro benchmark. who spends 100% of its time basically allocating and freeing. So if you were looking at a regular program, that spends what, 5 to 10% allocating and freeing, you're actually going to drop an order of magnitude more towards 1 to 2%, which is kind of what we're seeing in this box and benchmark. So expectedly, maybe, 2002 conclusions still hold. Per-class allocators are not really worth it still today. Now, switching to the region allocators, well, did that change? So in 2026, the speed up for region allocators is up to 14, 15% on 2 benchmarks, which is still relatively significant. Because again, especially again comparing the engineering cost, it's lower for region allocators than these per-class allocators. However, it's worth noting that the general purpose allocators have significantly caught up, right? In 2002, speed up was listed as at most 44%. Today, it's only 15%, which again, 15% is significant, but obviously it's less than 44. And so far we've talked about basically 2 costs, right? We've talked about the results for per-class allocators and for region allocators, and those results were mostly focused on the cost to allocate things and the cost to free those things. And in fact, there's one more cost to running with manual memory management, and that is, it's a little more subtle, is the cost of placement. And so let me explain what I mean by that. So when you allocate a set of objects with malloc, again, here's allocating, I think, about 10 objects with malloc, the pointers you get back from malloc represent a fixed region in memory. And so that fixed region is going to be the location of the object for its entire lifetime. And there's no way to change that or to suggest a specific other location. And so in this case, you hope that you'll end up in the left scenario where everything is kind of packed together and it might fit in, let's say, 2 cache lines if you assume one row is 1 cache line, versus the second case where everything is a lot more scattered. And so if you were in the first case, well, the first case will inevitably lead to better locality, better cache utilization, fewer cache misses, and therefore you'll get a faster program. So obviously you want to be in the first case. But unfortunately, if you use malloc and free, you don't have that guarantee. You don't know, things might end up in either one case and you have no control over that. And this is where region allocators can actually help, surprisingly. So again, here's a short snippet allocating n objects into a region allocator. And by construction, these objects are going to be packed together, right? Because region allocators have this mechanism of chunking allocations together, the objects will end up close together in memory. And so again, on top of the reduced operations, this is the second benefit of region allocators. They have these locality and contiguity guarantees. Now, here's the problem. How do you actually highlight this benefit, right? And so one problem that we found is that some of the benchmarks we used were short-lived. And so because they're short-lived, they don't actually experience a relevant level of fragmentation that, for example, long-running programs might. And so on this quick figure, you see whether you use naive or region allocation, if you start from a blank heap, meaning there's nothing there, things will be contiguous anyway, right? So in this, if you're just naively doing this, you're not going to highlight that contiguity guarantee that region allocations bring. So how can we highlight this property? Well, we developed this methodology that we named adversarial allocation, and which essentially is about putting garbage on the heap before the program starts. So we put garbage on the heap, which prevents the allocator from actually putting things anywhere it wants. And so you can think about it in a way similar to long-running programs, which might have a variety of lifetimes. And so things, objects might be interspersed between each other. And so here's a simple example. In this case, there's only 2 garbage pieces. And so what we also are able to do is increase the level of how bad can this fragmentation be before we start the program. So here's a relatively small amount of fragmentation. We can increase it to the second level, which is about double the occupancy of garbage in this memory area, or we can make it very extreme. And in this case, most of the memory is actually garbage, and the allocator only has access to a few spots to allocate its memory. So what are the results? Well, if you were using naive allocation, like I said, there is no guarantee of contiguity. So therefore, naive allocation is very sensitive to these fragmentation problems. And so in this case, it's up to roughly 70% for the parser benchmark at the worst adversarial allocation settings. On the other hand, region allocators, again, by construction, are resilient to this, and so they're virtually immune to any changes, right? What was 70% in the parser is 0% if you just use the region allocator in that program. And so again, this gives region allocators a lot of predictability in long-running programs where you care about tail latency, programs where you want predictable performance. Region allocators are able to give you that. So yeah, they provide resistance to heap fragmentation. So to recap, we've talked about per-class allocators. In 2002, they were not really worth it. Well, today, still not really worth it. We've seen that on this, with the best allocator on that benchmark, it was at most a 2% win. So given the high engineering cost in the general case anyway, probably not worth it. Region allocators, they could still provide up to 15% performance improvements, obviously depending on the program. It's worth, again, noting that general purpose allocators have significantly closed the gap between what was 44% in 2002 is now only 15%. And we've extended the methodology with a new method called adversarial allocation, which allows us to actually quantify how much more resilient are these region allocators to fragmentation. And so we saw that what could be, in the worst case, is 70% degradation in a benchmark is actually 0 if you use the region allocator in that benchmark. So with that, I want to thank of my collaborators, of course, Emery, who's my advisor, and then folks on Bloomberg with who we've had a lot of productive discussions on this topic. So I highlighted Josh, Frank, and John, but there's a few more. And thank you guys for your attention.
Cool, we've got plenty of time for questions.
Thanks for that. Great talk.
Thank you.
I may have missed it. You may have explained it, but just with the per class allocators, how did you actually implement that? I mean, for these large benchmarks like Clang.
So we selected, good question. We selected benchmarks that already had custom allocators, and essentially we took them out.
Cool.
So we didn't actually implement the per class allocator. It's already there, and then we have either we keep it the original version or we take it out. Right?
Great.
Maybe LLMs can do a whole implementation.
Great talk, thank you. I'm surprised by the way you summarized the old paper, because looking at the abstract and the conclusions, it basically says, well, custom allocation is bad, except for region allocation, but, and then it said multiple buts. It said region allocation is hostile to common programming patterns. It's all sorts of bad things, and then both the abstract and the conclusions, they actually say that, well, the big thing is that we introduce reaps, which are regions with the ability to deallocate a single object. So I was surprised that you didn't say anything about that. Can you say a little more?
Yeah, so correct. So first on the reaps part, it's true. So the original paper introduced reaps, which was a method to basically have region allocation while also trying to reduce the trade-off, which I'll get into in just a second, of higher memory usage. Reaps didn't really take off, right? You don't know about it today. And so that part of the paper was less successful than the part about reconsidering things. So it's true that in this talk I didn't mention the reaps part, but it's true that the original paper does mention this technique. Now in terms of trade-off, yes, region allocations, there is a trade-off, right? I actually have an extra slide about that somewhere. There you go. And so the trade-off is, well, you have a much higher memory footprint, right? Because you can't free until you're done, you have a higher memory footprint. And so this was measured from the original paper, and that's not very dependent on the actual technique. It's more dependent on specific programs, right? Depending on how the programs use the technique. So this was the measurement in the original paper, and which would be the same measurement today because, again, it doesn't really depend on hardware. And I think the peak is that for one benchmark, using region allocation makes the peak RSS 3 times bigger, right? But again, if you look at that benchmark, its memory usage was like, I think 10 megs or something. So times 3, 30 megs, right? It's not that big of a deal. But yes, the trade-off is definitely program dependent. And for some programs, if you have lifetimes that are equal to each other, then region allocations make sense. And if you don't, then maybe it's not a good strategy. In fact, that's a future direction. What if you could automatically, maybe with an LLM, I don't know, suggest locations where, well, maybe this function is a good candidate for region allocation or not, right?
Follow up from Yannis's question. Maybe would it be true that one of the issues with the REAPs is that actually implementing it was a methodological hurdle for you, because that would require some change. You explained in answer to my first question that the regions were already there. Implementing REAPs would have been a bit more non-trivial. Was that perhaps the blocker?
That's a fair assessment. I'd have to get back to you exactly on. I mean, REAPs hasn't been maintained in basically since 2002, so there would also have been. I'd have to take a look at it again and see if it's actually implementable today, etc. Well, yes, maybe the other challenge is there's going to be more implementation work there, right?
Yeah, but I was thinking, well, we now have ways of addressing that toil of implementing it, so it kind of would be cool to see that.
Yeah.
So another question has to do with multi-threading. So clearly, better locality is great for single thread, but it's really bad when you have fault sharing among multiple threads. So did you evaluate anything multi-threaded?
Good question. So we don't have, so most of our benchmarks are single-threaded. And the issue kind of is with how region allocators are typically used. So they're actually used a decent amount in multi-threaded programs, but they're typically used in multi-threaded programs in per thread mode, right? So you'd have a thread that has a region and it only uses that region anyway, right? So in terms of evaluation, it actually doesn't make that much of a difference, at least in that scenario. And if you had a region allocator that was thread safe, at some point you're writing a general purpose allocators, the more you add to it. So, so in that evaluation, it made sense to stick to single thread because of the way they're typically used, right?
Sorry, one last one. Again, a follow-up from Yannis's question.
We have time,
in terms of your contrast from the old times to now, surely that's one of the differences, right? Back in those days, many or most of our programs were single-threaded. Yeah, so many of our allocators were explicitly designed for single-threaded context, whereas now they have to be multi-threaded, right? And so that seems like a really fundamental shift in that period that's relevant to your work, right?
Yeah. So you're right, 2002 is, actually I used to have slides about this, but it eventually took them out. 2002 is exactly when the shift kind of happened from single core to multi-core. And actually when people started also having a third level cache. Before that, it was only 2 levels. And so it's true, and so again, we looked at a lot of modern applications. Clang is basically single threaded anyway, but Blender is multi-threaded, and again, it uses this per thread allocation. If you look at web servers, we were relatively unsuccessful in actually getting good measurements out of web servers because there's a lot of overhead in other parts of it. But web servers typically use custom allocators. For example, they have a region to process a request, and then when the request is finished, being handled, the region can just be disposed of. And so again, in basically every modern application I've looked at that use region allocators, it was a per thread, system. I don't think I've even seen one that was shared among things. So, but region allocators also give you these locality advantages, that would be an interesting direction in terms of evaluation. They give you the locality advantages per thread in a way, right? So you don't have false sharing. If ever your allocator was allocating things, interspersed and shared between threads, which most allocators don't do anyway. But again, region allocators provide you guarantees that this doesn't happen.
Time for one more question. Which I could get mine in if no one else. So one example of per class allocators that I've seen that does seem to be successful is in Python. So the Python objects, they keep around like 20 or 30 of every type of object. And the reason I think that one's successful is because it's keeping the objects already structured and already laid out and already like a bunch of initialization is done. So then when they recycle it, they just basically set a reference count and like clear a little bit of data. So I don't know if there's any cases like that you considered.
Good question. I didn't think of the Python thing. Good question. No, in terms of region allocation, actually I thought you were going to ask about the free list allocation, because in fact if you have the general purpose allocators makes a lot of use of these free list allocation in those scenarios. They actually make sense. But no, we haven't thought too much about. But it would be interesting. I'm interested to learn more about the region Python thing. So I'll look into it and maybe we'll have a chat later.
Okay, let's thank Nicolas.
Thank you.